Hello and welcome everybody to today's webinar on fertilizer production. This is the fifth webinar in our webinar series of the NUTRI-KNOW project. Glad you could all make it today. My name is Daniel. I'm from the European Science Communication Institute, or short ESCI, based in Germany. We have a very cold, foggy morning today. Hope you have maybe some more sun on your side, wherever you are right now. And yeah, today we will talk about fertilizer production. I have the honor of chairing this webinar, meaning I will look out for your questions. So feel free whenever you have a question during the session to just write them in the chat or use the Q&A tool, and I will have a look at them and then I will ask them at the best moment. However, should there be any unanswered questions from your side, we do have a community of practice set up, this being an online forum on our website. You can access it via this QR code, or you can just find it on our website. And there you also have the chance to ask questions, engage in discussions, or browse our knowledge base. So yeah, we have members, Q&A sections, and a knowledge base where you can have a look at all of the innovative technologies that we will be talking about today. And without any further ado, I give over to John in Ireland. So feel free to take control, John. And I hope the weather on your side is a little bit better today.
Good morning, everybody. No, the weather's no better over here. Thanks to the joys of being stuck on the left-hand side of Europe, out close to the Atlantic. But wet weather aside, firstly, you're welcome to the webinar. There's a number of us going to speak today, particularly in regard to fertilizer and fertilizer production and the NUTRI-KNOW project. But before we start, I was just going to give a quick overview of who we are, who is the NUTRI-KNOW project, and what are our goals. And we're a group of 11 partners from all across Europe, and we're together as part of the NUTRI-KNOW project with the main aim of broadening the impact of EIP agri operating groups in the field of nutrient management. We're trying to improve nutrient management practices, share the knowledge between the scientists and the end users, the farmers, and most importantly, trying to reduce the dependence on finite resources. So the 11 partners, there's 12 operating groups within the NUTRI-KNOW family. And like I say, our main objective is to reduce the dependence on finite or chemical and synthetic fertilizers and increase resource use efficiency. But why is the question? Why are we doing this? On the left-hand side of that slide there, you're going to see an infographic for the circular economy. And most people are aware of it, but by 2050, Europe has committed to becoming a circular economy. And the simple principle of this is that any resources which go into the economy, as little as possible of those resources after they're used and gone into production and recycled are leave that circular economy. You want it to return back into the production system. This makes for production challenges for everybody across Europe, but in particular for agriculture, as there's the information is shown, or research has shown, that with the growing population across the world, by 2050, we're going to need 3 planets worth of resources to provide food. Protein is an issue to keep the protein requirements for people. So there's going to be a potential scarcity of protein, as at the moment, 1 kilogram of protein requires 7 kilograms of nitrogen to produce on a plate. And there's finite resources, fertilizer resources and fossil fuel resources that are used to produce fertilizers. They're limited, and if practices don't change, we're going to be in trouble when it comes to trying to feed the population. So the emphasis from our groups here are on innovation, on new ideas. And across Europe, there's 1.5 billion tons of, on average, we'll average it out as 1.5 billion, because it's estimated between 1.2 or 1.8 billion tons of animal manures produced annually. Of that, in certain areas, like lower stocked areas like in Ireland, only no percentage of that is processed. But in other areas, like in the Po Valley and in Flanders in Belgium, there's very intensive livestock production, and up to 35% of agricultural manures are processed, and a large amount of agricultural waste and municipal waste rely on nitrification and denitrification of into the atmosphere of the nitrogen before the liquid from the digestate is released back into the environment to reduce pollution. And on the other side, there's somebody in a factory somewhere burning fossil fuels using the Haber-Bosch process to take nitrogen from the atmosphere and make it into a chemical fertilizer. So innovations like Giuseppe's going to talk about for struvite or Hongzen for manure are trying to capture those nutrients before the expensive process of it going into the atmosphere and then having to take it back out of it again happens. So just keep it in mind as the speakers are speaking, innovation in agriculture has been ongoing for millennia, from the very first guy who planted something, all the way through the changes in genetics, in agronomy, in modernization with mechanization. The driving force really is time, and the big one, it's money. If you were to look at this picture on the bottom right-hand side of the picture, there's solar panels in front of the tractors there. If we were having this conversation, maybe even 10, 15 years ago, there's a strong possibility that somebody will be saying about this new innovative technology coming along that potentially end users, farmers could use to save money and help reduce their emissions, which is PV solar panels. They're quite commonplace now, and that's only just because with the passage of time and the economic changes, it becomes more relevant. So on that note, I'll hand you over to Giuseppe, who's going to talk to you about struvite.
Thanks to John. Now, okay. I'm Giuseppe Moscatelli from CRPA. CRPA is a research center on animal production based in Emilia-Romagna region in the Po Valley in the north of Italy. And now will be illustrated a digestate treatment technology designed and implemented by Struvite Operational Group. Struvite Operational Group is one of the 12 engaged in the NUTRI-KNOW project. The problems the Struvite Operational Group wants to answer are the high P content in pig livestock soils, the ammonia emission from digestate during storage and application, and the nitrogen surplus in those areas characterized by high livestock density. To do this, the operational group designed a prototype at farm scale for extracting struvite. The struvite is a salt of ammonium magnesium phosphate. So the main goals of the operational group activity were to decrease nitrogen and phosphorus content in pig livestock digestate, to reduce emissions from storage and spreading, and also to facilitate the soil application of this treated fraction depleted in nutrients. And at the same time, recovering nitrogen and phosphorus as fertilizers for replacing chemical fertilizers in nutrient deficient area. Recovering nitrogen and phosphorus is the topic of this presentation. The struvite pilot plant was installed after the biogas plant of a pig livestock. The pig livestock is Colombaro Pig Farm, located in Modena in Emilia-Romagna region. And the prototype treated the digested clarified liquid fraction produced by screw press solid liquid separator. Digestate is an interesting matrix to be treated by this process and to produce struvite, because the anaerobic digestion mineralized a quota of organic phosphorus and nitrogen into orthophosphoric and ammonia nitrogen. These two forms are after usable to produce struvite. This is the layout of the treatment. The prototype is able to treat 0.2 cubic meter per hour, and the digested clarified liquid fraction from solid liquid separator is first slightly acidificated to decrease pH from 8.5 to 7.5 to increase the mineral orthophosphoric P form. After this acidificated fraction is microfiltered at 40 microns to partially remove suspended solid and organic matter that hinder the struvite crystallization. The microfiltrate fraction is then loaded to the struvite reactor, where crystallization and the precipitation of struvite take place. The struvite reactor is composed by two concentrical cylinders. In the internal cylinder is added magnesium chloride to facilitate crystal development. In the external one is added a base to increase the pH from the initial 7.5 to 10 to promote the struvite precipitation. The surnatant treated fraction depleted in nitrogen and phosphorus exit from the reactor on the upper surface, while the precipitate with struvite is discharged in a batch every 8 hours from the bottom. This is the installation and the photo of the prototype. This blue is the pretreatment acidification tank. On the left, we have the microfiltration unit, and on the right, we have the crystallization and the precipitation reactor. The P content in struvite precipitate is 6 times higher compared to P content of the microfiltrate fraction that enters in the crystallization precipitation struvite reactor. The nitrogen is 6 times higher, while the magnesium is 12 times higher compared to the microfiltrate fraction. The 37% of the influent P of the input digestate is recovered in the thickened fraction produced by the microfiltration. The 24% is recovered in the struvite precipitate. But if we consider between in and out in the struvite reactor steps, between the microfiltrate and the struvite precipitate, we can recover the 63% of the input phosphorus in this struvite precipitate. From the point of view of microbiology and the metals are expressed on the dry matter. The struvite precipitate produced is largely compliant with the limits set by the EU regulation. Since in this line red, since it is pig digested, only the zinc content is high, but fortunately in the future mandatory reduction in pig diet will reduce heat. The P content in relation to weight is low because the precipitate is characterized by over 80% of water, and once dried, the P content on weight also becomes in line with the regulation. These are the principal characteristics of the struvite produced chemical characterization. To conclude, struvite system to recover phosphorus and nitrogen from digestate, particularly from pig digestate, are technically feasible, but this treatment has still to be further more efficient. The project will continue with another funding program. The precipitate containing struvite should be used as raw material for the production of phosphate fertilizers to replace phosphate mineral rocks extraction. Fertilizer producer should collect this raw precipitate from several agro-livestock farms installation, refine and use it in their production to replace these phosphate mineral rocks. Because producing commercial struvite compliant with the EU regulation in the agricultural context could be problematic. And so I think that this final refinement and to produce a commercial fertilizer has to be applied by fertilizer producers. The high concentration of solid in the digestate, even if subjected to solid liquid separation and also to the microfiltration, is still a critical use. Now I finished and I leave the speech.
We have a question
Daniel.
for you, Giuseppe.
Okay.
I think it makes sense to ask that straight away. The question is all of the liquid fraction converted to struvite, or do we expect some loss? And could you maybe also give a rough indication on the amount of manure input to output expected from struvite production?
Sorry, Daniel, I don't understand the first part of the questions.
Is all of the liquid fraction converted to struvite, or do you expect some loss? That's the first part.
Okay. For this livestock farm, the solid fraction is not a problem because usually all the farmer in the Po Valley, and particularly where there is a biogas plant, have a solid liquid separator. And the solid fraction rich in nitrogen and phosphorus is not a problem because it can be transferred to Romagna regions or to land with deficient of nitrogen and phosphorus. The problem is the 90% of the volume of the initial digestate that is the liquid fraction. And so the goal of this prototype is reduce this nitrogen and phosphorus content in this liquid fraction that remain in the livestock farm to be applied to the soil. And so we concentrated our activity on the struvite precipitation from the liquid fraction. Of course, we lost a part of the phosphorus in the solid fraction.
But coming back to only the liquid fraction, in converting it to the struvite, is there some loss, some part of the liquid fraction that cannot be converted?
This is a prototype. And so at the moment, we treat only a few amount of liquid fraction.
Okay, then we have another...
No.
Yeah, sorry. Go ahead, Giuseppe.
No, the rest fraction not treated by this prototype now is stored in lagoon.
And another question towards the struvite. So you said it's technically feasible, but is it also commercially feasible? So can you give some information maybe on the financial details?
Okay, at the moment, this is only a prototype designed by the operational groups with the support of two industry of the region. At the end, I hope particularly one of these two company can make this prototype a commercial facility.
Mm-hmm. And one last question to you, Giuseppe. I think it's a question of understanding. Is the treated fraction with supernatant the clarified fraction?
Yes, the treated fraction is this supernatant fraction that is after stored in the tank and used in the soil for fertilizers uses.
And that's the same as the clarified. Okay, yeah. Okay, so I think then we can give it over to Hong then, I think, if I'm not mistaken.
Good morning, everyone. My name is Hong Zheng. I'm from Ghent University, located in Belgium. So yeah, it's also a foggy day today. Today I will talk about the nitrogen fertilizers recovered from animal manure and animal stable. And so firstly, as John already mentioned, manure is a problem in a livestock intensive region like Flanders. So the farmers are facing paradoxical scenarios. They firstly need fertilizer, need nutrients to grow crops, but in the meantime, they have surplus manure that cannot be applied due to the restrictions of Nature's directive that's only 170 kilogram nitrogen per hectare per year can be applied. This animal manure in a raw format, it can be applied on the farm and it can also be processed into different products to meet the requirement of application and machines. For example, the solid fraction can be processed into compost or solid pellets that's easy to be applied in broadcasting. And the liquid fraction of manure can also be processed into digested, concentrated minerals, or like ammonium sulfate, ammonium nitrate, these ammonium salts that can easily be applied through injection. In this case study of Renew, we use scrubbing processing technology to recover ammonium salts from manure, liquid fraction of manure. How it works? Firstly, from the liquid fraction of manure, we have the stripping compartments that air is brought into this compartment to recover the gaseous ammonia from the released from the liquid fraction, because ammonium in the solution form can be converted into a gaseous ammonia that due to an increase in pH or temperature. And then this ammonia gas is absorbed by acid solution such as sulfuric acid or nitric acid in the next compartment. In this way, we recovered ammonium sulfate or ammonium nitrate from the liquid fraction, and eventually there are the ammonia-free air can be recirculated in this system. So the product is ammonium salts in the form either in ammonium sulfate or ammonium nitrate. Both of them are liquid forms, and due to the composition of either nitrate or sulfate, the color is a bit different, but these are not affecting the efficiency or the application method. These products, they are slightly acidic and they have nitrogen content ammonium sulfate has nitrogen content 8%, and ammonium nitrate has a little bit higher because they are only nitrogen instead of sulfur in the other products. Both of them are pure minerals that has no organic particles. So eventually they can be applied easily through the injection machine. Also, because they are pure mineral, that means the mineral nitrogen to total nitrogen ratio is higher than 90%. In the meantime, we analyze the zinc and copper content in this product. They are lower than the limitations written in the EU fertilizing regulation. So according to the renewal criteria proposed by Joint Research Center, this ammonium sulfate, ammonium nitrate, can be regarded as a candidate renewal product, which means they can be used as alternative fertilizer to chemical fertilizers. But of course, this renewal criteria is still under discussion. So we still need to process with it. And eventually, the goal is to intake renewal criteria in EU fertilizer regulations. Yeah, like I said, because these ammonia salts, they are liquid, so they can be injected into soil when applying it to the farm. And in this way, the ammonia emissions can be reduced dramatically. And in this operational group, we also conducted 5 field trials in 2022 and 2023 with potatoes, maize, and winter wheat. And the results indicate that compared to synthetic fertilizers like urea or calcium ammonium nitrate, this recovered ammonium nitrate product has no significant reduction in yields or increase in nitrate residue after harvest. In some cases, this ammonium sulfate, ammonium nitrate can perform better than the reference using chemical fertilizers, because although this data is observed in dried condition, dried years, and the data has a little bit like relatively high heterogeneity, but it also indicates a potential that this product may increase the resistance of crop to abiotic stress such as drought. So currently, what the scenarios for the practice of manure is mainly we can only apply 170 kilogram nitrogen per hectare per year, and on top of it, to meet the requirement of the crop, we apply synthetic nitrogen fertilizer. In this case, we have surplus manure, but if we have renewal approved by the EU regulations, then we can recover the nutrients in the renewal products and replace the top-up synthetic nitrogen fertilizer using renewal products. And ideally, we will also have advance in the processing technology, meaning reduced processing cost. Because the renewal products, they are more pure minerals, so they have a more stable and consistent nutrient content as compared to animal manure. So these products are better or are preferred by the precision fertilization. So in the future, it's also possible that we use more renewal products in the January crop production. So ammonium sulfate can be recovered from manure. Also, it can be recovered from the animal stable by using an air washing system. Here is a case study of operation group gas loop. Over there, there is a problem of ammonium emissions in the animal stable, which harm the health well of the animals and also the workers inside stable. So there is more and more focus and necessity to improve or to develop technology and to reduce the ammonia emissions in the animal stable, and in the meantime to recover the nutrients in the form of fertilizer, so that it can also contribute to a more sustainable agriculture. Yeah, in summary, the main goals in gas loop operational group is to develop a pilot that can be able to clean the air in the stable and recover the ammonia from the livestock manure, and to reduce the ammonia emissions and produce a recovered fertilizer in the form of ammonium sulfate. In general, it will increase the animal and human operators' welfare and productivities because the better air conditions in this animal house. So how this air washing system works? Firstly, there is under the slotted floor of the animal house, there is a preset pump and pipe to suck the ammonia from the manure, released from the manure, and this ammonia is collected upwards to the system, air washing system, and so this ammonia will not go into the animal house where the animals is, but more collected in the solution that containing sulfuric acid. So then the ammonia is, when it's dissolved in the solution, is a base that can react with sulfuric iron that form the solution of ammonium sulfate. Then this process usually happens in a pH of 4.5, and then we use basically the solution that's containing sulfuric acid, and eventually this product is in a form of liquid. Also, there are some gas left out, which contains heat, so it can be reused during the cold seasons to heat the animal house. That can reduce the energy cost for the animal stable. But in the warm seasons, for example, in the summer, then this air is excreted into out of the house. The recovered product, like I said, is ammonium sulfate. This system has been monitored over 1 year. So during this year, it was achieved that nitrogen recover around 14.5 kilogram per liter of per ton of live weight of the animal. And it achieved avoids the ammonia emissions by 70.6 kilogram ammonia per year per ton of live weight. Also, sorry, because eventually we produced ammonium sulfate solution that can be used as a fertilizer, and so it's actually the productivity of this ammonium sulfate is around 230 liters per live weight per year, and the pH of the product is around 4, with a total nitrogen content around 6.4%, which 99% is ammonium nitrogen, and the total organic carbon content is around 1.3%. Although in the EU regulation, it's required that the total organic carbon content should be lower than 1%, but this can be achieved with a better management of the animal health and also improvement of the pellets. So eventually, this ammonium sulfate produced from this system can be used as a liquid inorganic fertilizer as required by the EU regulation in the PFC category number 1. Also, based on the calculation in these operational groups, this system can reduce the greenhouse gas emissions because by 66 kilogram carbon dioxide equivalent per liter per ton life weight per year. Because this ammonium sulfate produced from this system can be used as a replacement for the nitrogen produced from industries. In summary, this washing system can recover ammonium as a fertilizer and is technically feasible. The system has been reaching a technological maturity level equal to TRL 8. In the pig farm with a total life weight of around 1,000 tons, it can result in recoverable nitrogen 16.8 tons per year. And the nitrogen recovered as the ammonium sulfate solution can be used as a mineral nitrogen fertilizer to replace the synthetic fertilizer. Currently, the cost of this system can result in an increase of the meat produced by the farm around 77.3%, meaning 0.15 to 0.17 euro per kilo of live weight produced. This already considered the increased productivity in the farm and also the profile profit made from selling the ammonium sulfate fertilizer. So yeah, that's the end part of my presentation.
Thank you so much, Hong Sen. We have many questions for you. I think I will just take control and maybe go back to the respective slide so we can see it a bit better. The first one relates to the stripping and scrubbing process. I will just ask them step by step. The first one is digested a prerequisite similar to the struvite production for this process?
Yes, indeed. So like I mentioned here, we mainly use the liquid fraction to recover the ammonia from the manure because that is easier for air to go through the liquid parts, and usually the liquid parts of manure contain a higher mineral nitrogen content, which are better to increase the recovery rates of this system.
And do you know what the input-output ratio is from this process?
We have calculated not in this operation group, but in another study we have conducted. The recovery of total nitrogen is around 27%, and that's equal to around 30% of mineral nitrogen in total recovered as ammonium salts.
Mm-hmm. And the next question is, with the low pH, what would be the long-term effect on soil acidity? Could there be a problem?
So far, this is a new product and a new concept that we have not really conducted long-term experiment, so we cannot really certainly say it's no effect. But accordingly, we also see it could be a benefit. If you already see that your soil is a little bit organic, then you can or apply this fertilizer to neutralize the soil, because basically the crop needs a pH more neutral, from 6 to 7.
And the last, well, it's not the last question, but the next one is how much acids should be added to 1 cubic meter of manure? How does this process take place?
Yeah, I can search for the numbers of how the amount of acids added, but it also depends on the firstly depends on the animal type, meaning the ammonia, nitrogen in your manure, and then it's also depends on the scale of your installation. Sometimes the efficiency could be higher if you increase the air flow and also the recirculation of the fractions. Yeah, I can look for the numbers that we had in our case study and reply later.
Thank you. I think I will go to this slide for the next question. I think it's a very good one. It's about the recovered nitrogen from animal manure. How is it justified? Because in the end, nitrogen is nitrogen, whether it is recovered from mineral, recovered of mineral. So how is this justified then to go over the 170 kg per nitrogen per hectare limitation?
Yeah. So in this case, it's mainly refer to when you apply the nitrogen in the form of manure, or in the form of synthetic fertilizer, for example, urea or calcium ammonium nitrate, like that. I don't know if I understand correct or I answered the question.
Hello, I'm
So-
Prema. It's me who asked the question.
Yeah.
Can I jump in?
Yeah,
Because
yeah,
for
please.
me, it's really important to understand. For example, of course, it could be of interest for commercial companies, but we are talking about the livestock farmers in struvite or whatever technology that you're promoting here, right? So if it has to make real sense on the farm, it should also mean that the farmer can apply this added value fertilizer that you're recovering, because he puts a lot of effort and investment. This really comes with a lot of investment, and also the assets you're talking about. It also comes with a lot of education to the farmers on how they need to be very careful in applying. But potentially, it could also mean the animal welfare regards, right? So considering all this, and if the goal is basically to make use of your renewal product as a justification to say, okay, we can apply them on top of this 170 kg. For me, I don't understand. Still, even if they make this complicated processes, they spend energy and time and money, but it doesn't give the justification. So for me, the long-term goal would be bring down your livestock intensity based on how much hectare you have, full stop.
Yeah, so maybe I focus more on the product as a fertilizer, not really so much into in the standing in the view of a farmer. But thank you for the question to reminding this. Yes, actually the question raised from a surplus manure. So we don't say. Of course, there are some already some rules or some regulations saying the farmers need to reduce the density of the farm animals in the farm. But we are considering in the current case, if they don't reduce so much, if they still have quite some animals in the farm and they produce so much manure that cannot be consumed by his own or her own arable lands, then there are surplus manure they need to treat, and usually this was treated by some kind of wastewater treatment, denitrification, nitrification. But yeah, there is a way to convert into fertilizer that's will be able to use instead of costing money to treat this manure.
Maybe one comment from my side would be, I wanted that all the efforts that we put in here really brings value for the farmers, So I would basically compare what would be the cost of basically having this excess manure, whatever region it is, to kind of haul it to the nutrients deficit region. What is basically the cost versus this high investment in fancy peasy technologies, right? If it makes sense, basically you do nothing, put a cover in your slurry storage, therefore you have low emission, and then you ship it to other countries where there is more vegetable production. This would be, I think, yeah, I want to do a practical implementable solution. So in your cost analysis, I would also like to kind of recommend you, if this is something you can consider, is what is the cost just to treat the manure to ship to, say, 50 kilometers in the radius versus all this struvite and ammonium processing technologies? Thank you.
Yeah, thank you. Thank you for the question. Indeed, we have done a cost-benefit analysis for this installation. Basically, focus on the scraping and scrubbing system. Of course, because now we are more focused on the pilot scale, which could be a little bit higher than when you scale up or when there are more possibility of using the manure in different way. So the current cost, I already mentioned in previous webinars, and it's around 100 to 150 euro per ton of manure that we treated. And of course, it's based on the scale of your farm and the manure pressure in your region. So we also estimate that if the farm has a minimum 20,000 tons of manure produced every year, then that make more sense to have an installation in their farm to process the surplus manure into a product that can be used as a fertilizer to feed back to the crop. And this analysis will be updated when we have more updates from the renewal criteria that's being intaken by the EU regulations and also the advances in the processing.
Thank you so much, Hongzhen. We will just maybe quickly answer two more questions. The last one by Prema. Thank you also for unmuting your mic and asking, making these very valuable comments. But there's one remaining questions about the gas loop air treatment. Would you know how much sulfuric acid is roughly used per ton live weight per year for this treatment?
Okay, Hongzhen, if you want, I try to answer.
Great. Thank you, Christian.
The sulfuric acid required is only depending of the chemical equation. 1 kilograms of nitrogen recovered require 3.5 kilograms of pure sulfuric acid. Because we create an salt, ammonium sulfate, derived by the link of sulfuric acid with ammonia nitrogen. And so we have to make the calculation, because from 1 ton of live weight, we can produce 220 liters of ammonium sulfate at 6.4%. And so 1 ton of live weight produce 14.5 kilograms of nitrogen per year. And so multiplicating this 14.5 for 3.5 kilogram of sulfuric acid per nitrogen, we have around 50 kilograms of sulfuric acid per year used.
Okay, thank you, Giuseppe.
But Daniel, if you want, they can contact the NUTRI-KNOW project and ask this information. And so
yes, and
we can reply by mail. Is easier.
Yeah, exactly. It's a great comment. We can always give you the numbers via email or in our community of practice. I will give over to John now so that he has some time to also present his technologies. There's one remaining questions. Maybe Giuseppe Hongzeng, it would be great if you could answer that in the chat. There was a question about how the last number on this slide, the 0.15 to 17 euros per meter, was created. So if you could answer that in the chat, it would be great. Meanwhile, John, please take the floor.
Thanks very much, Daniel. And just quick reference back to the question there, which was comparing transport costs to the manure. Next week, the webinar, this is a gratuitous plug, is to do with transport by UFIC, and we'll be speaking about new technologies that can improve the logistics and the cost on management of manures. So I will get onto my slides, and I'm focused on grass juice and the production of fertilizer from the same and the product streams that go hand in hand with it. Firstly, I'm going to speak about operating group 9. This is grass to algae, and it's based in Flanders in Belgium, and it's on a pilot scale. And this group is harvesting low quality grass and processing an unused resource. It's a novel idea. It's on a pilot scale, but the grass juice produced is 40 to 60% of the grass weight. Then by further processes, the juice is refined down to promote microalgae cultivation, and it's providing a potential new income source for farmers. So what is it exactly? It's taking residual and low quality grass that's not traditionally used, like on roadside verges or green spaces and along field edges. It's a waste product up to this, and they harvest this and it's processed, and it's a simple process that the juice is extruded from it and there's a fiber fraction remaining, but we're concentrating on the grass juice here. And the grass juice is diluted down by 5 and 10 and 15%, and sedimentation is allowed to happen, and there's further pH adjustments which have to be made, and this is to increase the light penetration properties so that the fertilizer juice that's produced promotes good algae growth and reduces microbial contaminants. So in this trial, the microalgae species of Chlorella sorochinea grew better on grass juice after dilution to 5 or 10% as compared to the control, which was just the mineral medium. And this grass juice as a fertilizer for the microalgae was rich in micro and macronutrients, and it's a fertilizer for algae production. It's a very novel idea, especially to end users, farmers, telling them that they could potentially be growing algae. But in the tests that were done in this pilot scale, it shows potential for animal and food application of the protein, the algae that is being produced. And the algae biomass itself that grows in this liquid fertilizer contains 41% protein. So it's a new potential income source for farmers. Hongzhen knows a lot more technical information and details on it, so questions, she can answer question on it. But it's at a pilot scale. It needs to be investigated further, but it is a potential for using a resource that currently is just regarded as a waste and not used effectively at all. The last operating group from the NUTRI-KNOW family that I'm going to speak about today is based in the southwest of Ireland. It's operating group 10. It's called biorefinery glass. It's on a pilot scale as well. There's been a couple of different iterations of the biorefinery. It's literally just scaling it up. They have a figure of 8 tons per hour processing of fresh grass as the goal for where it's economically viable. So this was phase 3, where it was 2 tons per hour. It started at it started on smaller versions of the refinery, and since this there's been another version which has gone to 4 tons in the Netherlands. So it processes grass into 4 products. It refines unused protein that animals like ruminants don't normally use. They'll eat the grass, but the proteins and the nutrients in the grass that they cannot physically process are usually wasted. So the grass goes through an extruder, it's pressed, and 50% of the fresh weight of the grass goes into a press cake for ruminant animals. And this process, when it's all said and done, will increase the usable protein per hectare that's by 40%. And it will reduce nitrogen and phosphorus losses by 25% per hectare. So there's 4 different product streams. There's, in the top left-hand corner there, you have the high fiber press cake for ruminants that reduces greenhouse gases, but the yield remains the same. There was trials done in Holstein Friesian cows, early lactation for 6 weeks, and this is what the trial showed there. There was further trials done on pigs, where one of the product streams, so the first product stream is a high fiber press cake. The second one is refined from the liquid juice, and that's a high protein concentrate feed. It's 39 or 34% protein that can be fed to monograss. In this case, it was fed to pigs, and that increased live weight gain, reduced greenhouse gases, and reduced costs because it was substituting soya, which is traditionally brought in from South America, by a locally produced protein source. The third product stream is down here, and that's high value sugars. They're fructooligosaccharides, and they are a very high value product used as a prebiotic in animal foods. And most importantly for this webinar today, the last one on the left here is a slurry, a grassway slurry. And its nutrients, grassway fertilizer and its nutrients are actually, it says equal there to slurry, but they're a little bit better in some regards and a little worse than others. And here it is broken down. So on the left, you have your slurry, traditional animal slurry. So if we hadn't processed the grass and just gave it to the ruminants, to the cows, and went and analyzed it, this is what you would have been looking at. 72% K in the grassway fertilizer. After getting all those product streams, reducing greenhouse gases, reducing costs, you're still going to get 64% of your K. Your nitrogen percentage is going to be far higher. It's going to go from 15 to 29, and your P is about half. It's 7% as opposed to 13. Now these figures are for nutrient contents in kilograms per meter cubed of slurry or grassway. So the big question at the end of it all, with regards to grass to algae and biorefinery grass, is literally, is the juice worth the squeeze? Now in grass to algae's case, it's a pilot study, so it's limited. It needs further investigation as to regards the economics of it. But on the biorefinery grass refining in such a way, it comes down to scale. As I mentioned earlier, they've identified as 8 tons per hour of processing is necessary. The return on investment, theoretical return on investment, has been shown to be 3 years. There was a case study. It was an in-depth technical and economic feasibility study as part of the biorefinery glass operating group, and it showed a return on investment within 7 years. The employment potential in a rural area for a biorefinery model like the one I've discussed here today, it's a simple metric, but it's roughly 10% of your hectares. So for every 1,000 hectares, you're going it's 10% of your hectares. So they've estimated that if there was 1 million hectares, there'd be 100,000 extra jobs. But it's all scalable, and it's all to do with how getting up to a scale level and having them in fixed locations rather than a mobile unit like this. But the one underlying factor with regard to the biorefinery model that can produce a grassway fertilizer like this is the importance of the high value streams. The fructooligosaccharides essentially make it a more profitable endeavor and something that is economically viable with the costings of the inputs and the outputs that farmers are purchasing at the moment. I'm keeping an eye to the time, so I'll hand you back over to Daniel in case there's any further questions. Thank you very much.
Yeah, thank you so much, John. I think we will take maybe 5 extra minutes, go a little bit over time. Apologies for that. But thank you for all of these questions. So if you can raise your hand or type some questions up now. For those who have to leave, we will make this recording available shortly today or tomorrow. So you can also have a look at these last questions. But now we have one question coming in from Eddie already. This goes to Giuseppe, back to Giuseppe about the gas loop system. Would you know what is the not purified increased cost?
Sorry?
So this refers to the answer you gave. Where you said, so yeah.
Maybe I can explain
Yeah.
it
Yeah.
also. But I understood you said the net purified increased cost was 0.15 to 0.17, but there are also production profits, and there is also a profit from the selling of the ammonia sulfate. The question or the thing I would like to know is, what is the not purified cost, so without any other profit taken into account?
Okay, this cost of 0.15 euro per kilograms of meat is an increasing of production cost, because this device is able to reduce ammonia emissions and produce ammonium sulfate. But this kind of device has not to be seen as a device to keep money, because a livestock farm applied this device because it is mandatory from the industrial emission directive for the pig livestock over the 2,000 animal place of pig. And so when we have a big livestock pig farm, we have to adopt best available techniques to reduce ammonia emissions in the environment. And so this kind of device could be one of these best available techniques to reduce ammonia. And so we have not to see to make money, but to reduce ammonia emissions, to reduce environmental impact, and at the same time produce fertilizers. The cost of 0.15 euro per kilograms of meat is already purified from the incomes of the selling of ammonium sulfate. The price of this kind of ammonium sulfate is linked to the commercial price of the saline form of the ammonium sulfate pure at 21% in nitrogen content. Now the ammonium sulfate pure is around 350 euro per ton. And so this kind of solution is the 6% of this 300 euro per tons of ammonium sulfate. The two prices are linked because a farmer buy the nitrogen content of one fertilizer. But I'm replying in the chat to these questions.
Yeah, I hope that made it a bit clearer for you, Eddie. If not, feel free to reach out to us again. We're always happy to answer and follow up on these questions. And I think with that, I would like to close the webinar for today. There's one remaining question from Prema, but I think this is beyond this webinar anyway, so we will answer that in writing. So yeah, thank you all for participating today, for being engaged and asking all of these questions. Hope to see you in one of the following webinars. We have 2 more to go, one on transport and one on storage system. Yeah, thank you for being here today, and have a great remaining day. Thanks to the speaker, and hopefully see you soon. Bye-bye.
Bye, everyone.
Thank you. See you.